If you have the null hypothesis and the alternative hypothesis and a table of results like this, how would you interpret the p-value for the two scenarios in relation to the given hypothesis? Will you reject the null hypothesis or fail to reject the null hypothesis? Knowing how and when to do this is the objective of this video, and I will guide you all the way. Welcome to Titocan Solutions, and I'm glad to see you today. In statistical analysis, are you still confused about when to accept or reject the null hypothesis for fear of committing type 1 or type 2 error? Does the p-value still feel like a mystery to you? Well, you are not alone. Many beginners and even some researchers struggle to interpret p-values correctly. But today, I will break it down in a way that makes it simple, relatable, and practical, just how we do things here at Titocan Solutions. So today, we are going deep into one of the most misunderstood areas in statistics. That is unraveling the mystery of hypothesis testing, especially focusing on understanding null and alternative hypotheses and interpreting p-values in various tests. Whether you are a student, researcher, or analyst, understanding when to accept or reject the null hypothesis can be confusing, especially with all the rules and jargon. But don't worry, by the end of this video, you'll be able to understand the core concepts and interpret results confidently. My name is Titocan, and this is Titocan Solutions, a YouTube channel that improves the knowledge of how to do things. Now, let's get started with the basics. What is null hypothesis? The null hypothesis is a statement that is being tested in statistical analysis and acts as the default or baseline statement of the position of things that a statistical test attempts to challenge with sample data. The former statement is that there is no effect, no difference, or no relationship between variables in a population. It assumes things are the same, normal, or not related. Typically, the null hypothesis plays four basic roles in statistical analysis. 1. It provides framework for testing. For this, the null hypothesis provides a clear statement that can be tested mathematically and sets the stage for statistical inference by defining what we assume to be true unless there is strong evidence against it. 2. It provides basics for comparison. That is, when we compare any statistical test, such as one sample t-test, independent sample t-test, ANOVA, correlation, and regression analysis to measure by the field, we compare the observed data against the scenario described by the null hypothesis. This comparison helps determine whether what we observe is due to chance or a real effect. 3. It controls for bias. The null hypothesis provides the assumption that nothing unusual is happening by assuming that the null hypothesis is true. For example, if you are testing whether a new drug improves blood pressure, the null hypothesis will be that there is no difference in blood pressure between those taking the drugs and those not taking it. By providing this statement as the starting point of the analysis, we reduce the risk of jumping to incorrect conclusions and avoid the temptation of committing type 1 or type 2 error. On this basis, it is only when the data show a statistically significant result, usually when the p-value is less than the significance level of 0.05, do we reject the null hypothesis in favor of the alternative hypothesis. In doing this, the null hypothesis truly controls for bias. And 4, it drives decision making. The outcome of a hypothesis test is to either reject the null hypothesis or fail to reject the null hypothesis. This outcome guides researchers, scientists, and decision makers in making the appropriate decisions. Now, let's move to the alternate side. What is alternative hypothesis? The alternative hypothesis is a statistical concept in hypothesis testing. It serves as the counterpart to the null hypothesis and represents the outcome that the researcher or analyst is hoping to support with evidence from the data. It is a statement that there is an effect, there is a difference, or there is a relationship between variables. It challenges the default assumption of the null hypothesis and suggests that the observed results are not due to chance alone. Typically, the alternative hypothesis plays four basic roles in statistical analysis. 1. It guides the purpose of the test. That is, while the null hypothesis acts as a baseline, the alternative hypothesis defines the specific research question. It represents the idea you are testing for. For example, if you are testing whether a new drug improves blood pressure, the alternative hypothesis might claim that the new drug is more effective than the current treatment. That is, there is difference in blood pressure between those taking the new drug and those not taking it. 2. It determines the direction of the test. That is, the alternative hypothesis influences whether a statistical test is one-tailed or two-tailed. For example, alternative hypothesis is right-tailed if the population mean is greater than the hypothesized value, or is left-tailed if the population mean is less than the hypothesized value, and it is two-tailed if the population mean is not equal to the hypothesized value. 3. It wins when the null hypothesis is rejected. When data provides strong enough evidence, such as when p-value is less than 0.05, to reject the null hypothesis, it favors the alternative hypothesis as the more plausible explanation of the results. This means we are concluding that something meaningful or statistically significant is happening. And 4, it drives innovation and discovery. What this means is that the alternative hypothesis allows us to test new ideas, challenge old assumptions, and make data-driven conclusions that can lead to advances in science, business, medicine, and many other fields. It pushes research and innovation. Now, what is p-value? P-value is the probability value that tells you how likely it is that your data could have occurred under the null hypothesis, and is a measure that helps you determine the strength of evidence against the null hypothesis. It does this by calculating the likelihood of your test statistic, which is the number calculated by a statistical test using your data. Essentially, the p-value plays two basic roles. 1. The p-value quantifies uncertainty. That is, the p-value gives a probability that your sample data would occur under the assumption that the null hypothesis is true. And 2, it is a decision-making tool. That is, it helps you to decide whether to reject or fail to reject the null hypothesis. A p-value less than or equal to 0.05 means the observed result is unlikely under the null hypothesis, suggesting strong evidence to reject the null hypothesis, while a p-value greater than 0.05 means the result is likely under the null hypothesis. So in this case, you do not have enough evidence to reject it. Now, to better understand the three statistical concepts that we just spoke about, I want you to think of it like a courtroom where a criminal suspect is brought before the court for justice. In this case, the null hypothesis assumes the accused criminal is innocent, and the alternative hypothesis suggests the accused is guilty. The only thing that can set the suspect free or find the suspect guilty is the evidence, which is your data. Your data has to be strong enough with the appropriate probability of obtaining the observed result to reject the null hypothesis. Otherwise, the criminal will be set free as an innocent person. This is where the p-value comes into play to test the statistical significance. However, there is a general rule that guides the statistical application of p-value that you must commit to your statistical heart. The statistical guideline is as follows. If the p-value is less than or equal to 0.05, there is statistically significant difference, and the statistical decision will be to reject the null hypothesis. Otherwise, if the p-value is greater than 0.05, there is no statistically significant difference, and the statistical decision will be there is no sufficient evidence to reject the null hypothesis. So we will fail to reject the null hypothesis, meaning we should accept the null hypothesis. Now, as we proceed in this tutorial, you will continue to hear the phrase reject the null hypothesis and fail to reject the null hypothesis. So it's important that you know what this phrase means. Reject the null hypothesis means that based on your data and the statistical test you ran, you found sufficiently strong evidence to conclude that the null hypothesis is unlikely to be true. In plain terms, you believe there is a significant effect or difference, or that there is a relationship, whereas fail to reject the null hypothesis means to accept the null hypothesis because your data does not provide enough evidence to confidently say the null hypothesis is false. Importantly, this does not mean the null hypothesis is true, just that you don't have sufficient proof against it. In plain terms, it means there is no significant effect or difference. Now, to practically understand the concept, I will present the hypothesis and some numeric examples of p-values for selected statistical tests, and then show you how to interpret the p-value and the hypothesis, putting into consideration what we have learned so far. One sample t-test. One sample t-test is a statistical technique that is used to compare the means of one group against a known mean. I have published a detailed video on this topic with practical demonstration of the analysis in SPSS, and it's on my YouTube channel at Titocan Solutions. Please check the link in the description section to see the video. Now, let's assume the test value is 100, which is a known value. Then, the hypothesis for this type of analysis will be as follows. The null hypothesis states that the population mean is equal to the test value, while the alternative hypothesis states that the population mean is not equal to the test value. This is usually written like this, where 100 is the test value. If, for example, you have done the analysis with a given set of data and variable x, and the result outcome is as shown in this table for two different scenarios x1 and x2 respectively, how will you interpret this type of results, putting into consideration what we have learned so far? What does the p-value say about reject the null hypothesis or fail to reject the null hypothesis in relation to the sample mean and the test value? How to do this interpretation is actually the objective of this tutorial, and I will guide you through as we proceed. In this table, the test value is the known mean value that you are comparing your data with. The sample mean is the mean value that you have calculated from your own data, while the p-value is like the judge and jury and the determinant of whether the results from your sample data are statistically significant, which is used to reach a decision whether to reject or fail to reject the null hypothesis. Now, in scenario 1, with variable x1, the sample mean is 107 and the p-value is 0.03. As you can see, the test value is 100 and the sample mean is 107, which is 7 units greater than the test value. Obviously, there is a visual difference, but unfortunately, you cannot statistically say that the sample mean is greater than the test value, and you cannot also say the difference is statistically significant until the probability that it didn't occur by chance is proven. The only way to prove this is to assess the p-value as the judge and jury in this case. As you can see, the p-value for variable x1 is 0.03 and is less than 0.05. So, according to the general rule, if the p-value is less than or equal to 0.05, there is statistically significant difference. It is only at this point that you can agree that there is difference between the sample mean and the test value. Now, the decision to take at this point based on the hypothesis will be to reject the null hypothesis, indicating that the sample mean, which is 107, is significantly different from the test value or population mean of 100. This shows that there is evidence the population has changed, and it is unlikely that the 7-point difference occurred purely by chance. Now, in scenario 2 with variable x2, the test value remains 100 and the sample mean is 102, with observed difference being only 2 units. The p-value for this comparison is 0.08. As you can see, the sample mean is 102 and is still greater than the test value of 100. Though there is also a visual difference, but unfortunately, you still cannot statistically say that the sample mean is greater than the test value, and you cannot also say the difference is statistically significant until the probability that it didn't occur by chance is also proven. As usual, the only way to prove this is to assess the p-value as a judge and jury again. As you can see, the p-value for variable x2 is 0.08 and is greater than 0.05. So according to the general rule, if the p-value is greater than 0.05, there is no statistically significant difference between the compared entity. This means that even though the sample mean is 102, it is not significantly greater than the test value or population mean that is 100. The sole reason for this is because the p-value is greater than statistical threshold of 0.05. So basically, what this scenario means is that the mean of 102 as provided by your data is not statistically significantly bigger or greater than the test value or population mean of 100. Then, the statistical decision based on this hypothesis will be that we do not have sufficient evidence to conclude that the population mean is different from 100 based on the data available. So we fail to reject the null hypothesis because there is no significant difference, meaning the test value or population mean could still be 100. This shows that there is no change in the mean value, and though there is a visual change, it is likely it could have occurred due to chance, such as sampling variability or random error, rather than reflecting a real difference in the population. Basically, these two scenarios illustrate a vital point in hypothesis testing. That is, even if a sample mean is numerically different from a test value, only differences supported by a p-value less than 0.05 are considered statistically significant. On the other hand, the magnitude of the difference, the sample size, and the variability in the data also contribute to whether the result will reach statistical significance. Now, let's proceed to another test statistic, the independent sample t-test. The independent sample t-test is a statistical technique that compares the means of two independent groups like male and female groups. I also have a detailed video in my YouTube channel at Titocan Solutions where I made a hands-on practical demonstration of how to perform the analysis in SPSS and gave a full interpretation of the analysis results. Please check the link in the description section to see the video. Now, let's take a look at the statement of hypothesis for independent sample t-test. The null hypothesis states that the means of both groups are equal, while the alternative hypothesis states that the means of both groups are not equal. This is usually written like this. Again, if for example you have also done the analysis with a given set of data consisting of the weight of male and female gender to determine whether the observed difference in the weight is significant or simply a result of random variation, and the result outcome is as shown in this table for two different scenarios. How will you interpret this type of results, putting into consideration what we have learned so far? What does the p-value say about reject the null hypothesis or fail to reject the null hypothesis in relation to the weight of the male and female gender? Please take note that the method of interpreting the results in this table is not entirely different from the previous example, but in this case, we are comparing the average weight between male and female gender groups. Now, in scenario 1, the reported mean weight for males is 75 kg, while for females, it is 70 kg. The difference between these two means is 5 kg. The p-value obtained from the independent sample t-test is 0.02. Now, according to the general rule, if the p-value is less than or equal to 0.05, it indicates there is statistically significant difference. As you can see, the p-value is 0.02, and this is less than the standard significant threshold of 0.05. This therefore would imply that there is statistically significant evidence to conclude that the average weight of males is different from that of females in scenario 1 sample, meaning that gender has a significant effect on weight. By virtue of this, the statistical decision will be to reject the null hypothesis. In practical terms, this means the observed difference in weight is unlikely to have occurred by chance alone. Therefore, we reject the null hypothesis, which assumes that the means of both groups are equal. implying there is no difference in the mean weight between males and females. The result supports the alternative hypothesis that states that the mean of both groups are not equal, implying there is a significant difference in average weight based on gender. In scenario 2, the average weight for males remains at 75 kg, while the average weight for females is now 74 kg, which is just a difference of only 1 kg. The p-value for this comparison is 0.31, which is greater than the standard significant threshold of 0.05. But according to the general rule, if the p-value is greater than 0.05, there is no statistically significant difference. This result suggests that the difference in weight between the male and female groups is not statistically significant, meaning that there is no significant difference in weight. The 1 kg difference observed is small and could likely be attributed to random variation or sampling error. As a result, we fail to reject the null hypothesis, which indicates that there is no meaningful difference in the average weights of the two groups. Practically, this means we do not have enough evidence to say that gender plays a role in determining the weight in this particular sample. The data do not support the claims of a significant weight difference between males and females in this context. So, we accept the null hypothesis or fail to reject the null hypothesis. Now, let's move on to the next test. Pearson's correlation analysis. Pearson's correlation analysis is a statistical technique that determines the strength and direction of a linear relationship between two continuous variables. There is also a full video on this topic that I have published in my YouTube channel at Titocan Solutions, where I demonstrated the analysis procedure in SPSS and interpreted the entire results. The link to the video is also given in the description section. Now, let's take a look at the statement of hypothesis for Pearson's correlation coefficient. The null hypothesis states that there is no linear relationship between the variables, while the alternative hypothesis states that there is a linear relationship between the variables. This is usually written like this. Here, the alternative hypothesis implies that the correlation could be positive or negative, and these indices have their implications, and you will understand them better as we proceed in this video. Similarly, if you have also done the Pearson's correlation analysis with a given set of data consisting of two continuous variables such as hours of study and exam scores to determine whether there is observed significant relationship or correlation between the variables, and the result outcome is as shown in this table for two different scenarios. How would you interpret this type of results, putting into consideration what we have learned so far? What does the p-value say about reject the null hypothesis or fail to reject the null hypothesis in relation to the correlation coefficient? In scenario 1, the correlation coefficient is 0.82, and this is positive. This result shows a strong positive correlation between the number of hours students spend to study and their exam scores. In practical terms, the positive coefficient indicates that as the number of hours students spend to study increases, the higher their exam scores tends to be. On the other hand, the p-value is 0.000, which is well below the significance level of 0.05. According to the general rule, if the p-value is less than or equal to 0.05, there is statistically significant difference. This means that there is a statistically significant relationship between the two variables. So by statistical decision, we will reject the null hypothesis because the relationship observed is statistically significant. In scenario 2, the correlation coefficient is -0.12, and this is negative. This result shows a very weak negative correlation between the number of hours students spend to study and their exam scores. In practical terms, the negative coefficient indicates that as the number of hours students spend to study increases, the lower their exam scores tends to be, indicating a potential drop in exam scores. On the other hand, the p-value is 0.285, which is greater than the significance level of 0.05. So according to the general rule, if the p-value is greater than 0.05, there is no statistically significant difference. This means that there is no statistically significant evidence that there is a linear relationship between the two variables. So by statistical decision, we will fail to reject the null hypothesis because the relationship observed is not statistically significant or meaningful as it could have occurred by chance. This simply means that we should accept the null hypothesis. Finally, regression analysis. Regression analysis is a statistical technique that is used to predict the value of a dependent variable based on one or more independent variables. In a simple linear regression, the linear equation generally used is this, where y is the dependent variable or the outcome variable, a is the intercept, b is the regression coefficient or the slope, x is the independent variable or the predictor variable, and epsilon that looks like e is the error term. In this equation, the key statistic is the regression coefficient, which measures the magnitude and direction of the effect of the independent variable on the dependent variable. In this equation, the regression coefficient or slope indicates how much the dependent variable changes on average for each 1 unit change in the independent variable. You will understand all of these definitions better when you see the full video I have published on regression analysis with a hands-on practical demonstration and interpretation in SPSS. The video is on my YouTube channel at Titocan Solutions. Please check the link in the description section to see the video. Now, let's see the statement of hypothesis for this type of analysis. The null hypothesis states that the independent variable has no effect on the dependent variable, that is b is equals 0, while the alternative hypothesis states that the independent variable has an effect on the dependent variable, that is b is not equals 0. This can be written like this. Again, let's assume you have done the regression analysis with a given set of data consisting of dependent and independent variables, and the result outcome is as shown in this table for 2 different scenarios. As usual, how would you interpret this type of results? Put into consideration what we have learned so far. What does the p-value say about reject the null hypothesis or fail to reject the null hypothesis in relation to the regression coefficient? As you can see in this result table, the dependent variable is body weight, while the independent variable is the daily calorie intake. In scenario 1, the regression coefficient b is 0.03, showing that for every additional 1 kilocalorie consumed daily, body weight increases by 0.03 kg on average. The p-value is 0.004, and according to the general rule, if the p-value is less than or equal to 0.05, there is statistically significant difference. As a result, the p-value of 0.004 indicates that the result is statistically significant. Therefore, we will reject the null hypothesis and conclude that calorie intake significantly affects body weight. This suggests a clear predictive relationship where diet management could influence weight control strategies. In scenario 2, the regression coefficient b is 12.50 kg, showing that for every additional 1 kilocalorie consumed daily, body weight increases by 12.50 kg on average. The p-value is 0.114, and according to the general rule, if the p-value is greater than 0.05, there is no statistically significant difference. This indicates that the result is not statistically significant in the model. Therefore, we fail to reject the null hypothesis and conclude that calorie intake does not significantly affect body weight. This is also a clear predictive relationship where diet management could influence weight control strategies. Although there may be a trend, unfortunately the data do not provide sufficiently strong evidence to confirm this with confidence. This means we should accept the null hypothesis. So, what's the big takeaway now? Always remember to start with your hypothesis. Use the p-value as a decision factor in every statistical test. When p-value is less than 0.05, you should reject the null hypothesis. But if it is greater than 0.05, you should accept or fail to reject the null hypothesis. Remember, statistical significance does not always mean practical significance. And finally, you should always interpret your data results in the context of your study. But right now, we have come to the end of this video, and I am optimistic you will be able to replicate the methods and procedures in this video as guideline to interpret your p-value results and decide whether to reject or fail to reject the null hypothesis. If this video has helped to simplify hypothesis testing for you, go ahead and click that like button, share this video with others, and subscribe to Titocan Solutions, a YouTube channel that improves the knowledge of how to do things. For private tutorials, collaborations, or help with your research project, reach out to me via email at asktitocan@gmail.com. I am here and available to work with you. Thanks for your time and subscription. Thanks for liking and sharing this video to others. And thanks for seeing this video to the end. I look forward to seeing you in the next video. Bye.